Okay. It's a great pleasure to have Pratik for this series.
Thank you. Firstly, thanks everyone for being back for the fourth edition of this thing. So, let me just recap a little bit what we were saying last time, just so that everyone's.
I think the attendance is better in the fourth edition than the first.
Yeah, maybe it got better. Yeah. Oh, actually, on that note, another thing was a lot of people have motivated me to write lecture notes for this, including people not here. So, if there's any student who's interested in helping me out with it, that would be nice. Like that would make my life easier.
Yeah, that's a great idea. Hey, someone step forward.
Okay, so we can talk. If you're interested, then you can talk to me later. Okay, so let me just review a little bit what we were talking about last time. So largely we were talking about this Marolf-Maxfield paper, and so here's the reference actually, which I didn't give last time. Okay, so what we defined last time was a closed universe Hilbert space. So the states were defined as follows. The states were superpositions over what we call these Z of J states. By I. Each of these J's was like some asymptotic boundary condition with some sources J. We turned them on in the Euclidean past, and then we evolved that to cut it open at some point. So the picture was we have some number of universes here. And we cut it open at some slice where we are not cutting through any asymptotic boundaries. That's defining some state of finite volume universe here, and that's our closed universe.
I see. And sorry, I didn't realize not cutting through any asymptotic boundaries. So that means in the AdS context also, when the discussion is applicable, you would then be defining a closed universe.
Yes. So it's very important. At this point, we're only defining a closed universe Hilbert space. We'll talk about open universes in a bit. For now, it's just this. Okay. And these were the states. For a Hilbert space, we also need an inner product. The inner product is defined basically by, so if I want to look at the inner product, we'd say Z of J1, Jn, Z of J tilde 1, J tilde M would be fairly general. This is just given by the path integral that computes the. So here we think of these as circles or closed boundaries in the Euclidean past. So these are all J1 tilde, J tilde M, and then these are all thought to be in the Euclidean future. So somewhere here, and then we're defining the inner product by just gluing things together. Using the gravitational path integral and assigning a weight given by the standard action. So here, each of these, the only difference between the ones in the Euclidean past and future is we have some complex conjugation. So this is going to be Z of J1 star, Z of Jn star. So this here, the angle brackets just means do the gravitational path integral with those boundary conditions. So that defines an inner product. Once you have the states and inner products, you can construct a Hilbert space. An important point here was that we'll have to quotient by null states. There could be states with zero norm. We can remove them. That will lead to some drastic reduction of the total Hilbert space, and it can be pretty drastic. So what we found was we labeled the Hilbert space by what we call these alpha states. The alpha states were defined by. So firstly, we defined an operator Z hat, which creates one of these circular boundaries in the Euclidean past, and so Z hat of J acting on alpha was defined. So these alphas were basically eigenstates of these operators. It was important that all of these Z hats commute with each other. So if you can simultaneously diagonalize them. And then we just found alpha to be simultaneous eigenstates of all of this. This is just Z alpha. J. This is true for all J. So for all J, this basically outputs some number.
And J was specifying
the sources on the boundary. Very good. Given this, we now have an interpretation for what the path integral can do. So any path integral of this kind is just by using this alpha state decomposition, we can just write it as sum over alpha P alpha, Z alpha of K1, Z alpha Kn. So this is just coming from inserting a complete set of states here. So these are all the eigenvalues corresponding to alpha, and P alpha is, you can think of as a probability. It's the overlap between the Hartle-Hawking wave function normalized appropriately and the alpha state normalized appropriately. Okay. So these P alphas are basically like probabilities. The Hartle-Hawking state is just the empty state. So you should imagine the state where we've not inserted any asymptotic boundaries in the past at all. Which is the standard thing, which is the no boundary state.
And Pratik, just in terms of visual representation, I should think of, say, an alpha state as a linear combination of the Hartle-Hawking, the no boundary, one boundary, two boundary, some suitable.
Yeah. So this
infinite number of such terms.
Yeah. So a priori, we don't know that much about what it looks like, because it could be, for example, that the reduction in number of states is so drastic that secretly there's only one state left. In which case the Hartle-Hawking state is secretly gauge equivalent to whatever alpha. So the Hartle-Hawking state itself is an alpha state in that case. But in general, the expectation should be that we are left with some, at least from the gravity side, we're left over with some set of states, and those would be labeled by something. So for example, simple models to think about are these 2D models where, for example, in the Marolf-Maxfield model, it would be of the type you said, where it's a superposition over universes, over different numbers of universes. So it could be a superposition between 0 universe, 1 universe, 2 universe, and so on, with some weights. But it's finely tuned such that it's exactly an eigenstate of C of J.
And just out of curiosity, does the area make sense in JT, in AdS?
Yeah.
And
in JT as well, it makes sense. It's a little less well defined in the sense that, so Marolf-Maxfield is like perfectly finite. In JT, there's this issue of we only understand JT as an asymptotic expansion in this genus expansion. You need a completion for it. But if you could make sense of that completion, morally speaking, the different alpha states would be labeled by the different set of matrices on the boundaries. The choice of Hamiltonian on the boundary would be one for each of them. So it's a continuous set of all of this. So it's going to give you some.
Those P alphas were
the weights. Exactly. These are just the weights in the matrix.
But, and there we expect an infinite number of states, right? Despite the overlap.
Because
you need this sum.
Right? Yeah.
So we went through this last time, but just to be clear, on the string, if I think of the string world sheet as a 2D gravity theory, then are these alpha states psi of xi, where xi are the xi of sigma? Are these Schrodinger wave functionals of xi of sigma?
Of xi of sigma. So all this.
BRST invariant versions of those.
X.
All physical states you would define on closed string.
It would be all the gauge invariant boundary conditions you could set up to.
But I was trying to. So would it literally be that I would have a wave functional of xi of sigma?
There was some confusion last time about this Fock space versus not Fock space issue. Forgetting that, yes, I think so. I would say so.
Okay.
Psi of xi. Whatever it takes.
Psi of xi of sigma.
Whatever makes.
So that is equivalent to also psi of x of all the different fields. Right? Because you can Fourier transform that x of sigma. And so the various psi of x for each oscillator.
Yes, I think so. That's right.
So that
their alpha is like the different oscillators.
Alpha is different oscillators and the location of all the oscillators.
And the location.
That would be like a string field.
Yeah.
Is it Z the analog of the string?
Z is the analog of the string field, but that Z generates the whole Hilbert space.
And then I thought alpha was an eigenset.
That's right.
Then alpha would be like an eigenset.
If you mean precisely, I thought you meant just like the set of states is.
Shiraz was trying to understand what are the different J's.
Precisely what that is.
Was that what you were saying?
Yeah, I was saying in the spirit that if you have, let's say, one scalar field, you have a phi hat operator, which is fine. But then you also have states which are such that phi hat on state is phi on state.
Yes.
Schrodinger wave function.
Yes.
Eigenstates in Schrodinger wave function.
Yes.
So this would be like that with the eigenstates of Schrodinger wave function basis of string field.
Yes.
Is that right?
Yes.
Eigenstates of the string field.
Yeah. Of yes.
Of Z or alpha, whatever.
Z.
Alphas. The eigenstates
Both, I guess. I guess you're talking about this operator and the corresponding.
Are you quotienting by the null states or before quotienting?
No, at the moment, just doing the naive thing, classical string theory at the moment.
Oh, I see that.
Yeah. My next question was going to be that. Now, do you expect that when you work out this inner product here, do you have a physical there are two possible physical expectations. A, the Fock space of everything.
Yeah.
B, the Fock space of only gravitons. Which of these is your expectation for? Or C, and something I'm not thinking
else.
Why only gravitons? String theory.
Because last time we had this discussion that the other states decay to gravitons.
Oh, I see. Some stable states.
Yeah. So, in some sense, at finite energy, not finite energy density, but things like that. At finite energy, you wait long enough, you only see gravitons.
Yeah, it should certainly only correspond to all stable particles, I think. I think unstable particles shouldn't be part of this.
So that's what I mean by gravitons.
So that I think should be. Now, when you add interactions, maybe there's a further reduction or something, which
I was thinking you needed interactions for this reduction. Because without
so that's why I'm not sure if it's just that. It could be a further reduction. I'm just saying, like, for example, in these simple models, there's a reduction further than what you may think.
But then we should, if there is a further reduction, we should have an interpretation of that in the bulk. And there we don't imagine that there is a further reduction. I mean, the Fock space of gravitons is correct. At large distance.
If anything, this would be only visible at non-perturbative level. Like perturbatively, you would never see it.
But even non-perturbatively, we believe in type 2B theory. Fock space of gravitons at large distances is exactly correct.
For that reason, you might expect it's the same as the Fock space of gravitons. If that's correct.
But then is the expectation that you implement this procedure and this classical Hilbert space, which is huge, gets cut down to just the Fock space of gravitons?
Yes.
Well, if that's the expectation, it should be pretty possible to implement it in worldsheet string theory.
Should be.
And it sounds like a cool application of this, right? Because it's very abstract here.
Right. So
there's very concrete, very familiar.
So there's a version of that thing which was done for like world line theory. So it's like simpler version of that, where like by Marolf-Maxfield and others, maybe Mukund, where they tried to do that, but better version would surely be the
and do they see this analog? But they probably don't see the analog of this reduction, right?
Because put in interactions and so on. I don't think they put in any interactions. That's as far as I can tell. I don't know if they put in interactions.
But the interactions are sort of singular world line. You put them by hand.
There's nothing singular. Once you go to QFT.
I agree. I just don't think they will have done that.
I'm not sure they did that. I don't know in detail. So, but it seems like a natural thing to try. Given this formalism, just apply it to that and see what it means.
But this has been around for many years, right?
This has been around for 5 years, 6 years.
But nobody's tried to do this.
As far as I can tell, no.
There's no interest in turning cartoons into equations.
I don't know.
I'm not even totally convinced by what you said in response, Pratik. Maybe I'm just slow because the concept of decay, Shiraz, that you have in mind is the space-time concept, right?
Yes.
100% sure. Sorry.
But these asymptotic boundaries, roughly, I'm thinking of as things that live for a long time, right? Like these are like.
Yeah, but I'm just trying to distinguish, 2D from target space, as in. What I'm saying is, if I were just thinking as a 2D person, I would say, okay, what are the states you can create in the CFT by inserting vertex operator? Those are the analog of your Z of J's. So all physical states, let's say, right, meeting all the conditions, are what you can create. Now, if a state in a space-time sense can decay,
why does that?
That means there is a amplitude where a well-defined single universe state can become two single universe states. Does that mean a cut down in the worldsheet sense? I'm not fully sure.
I'm not sure either, but it does impact his inner product.
Absolutely, because
there would be diagrams
non-zero
connecting
inner
them.
product between these two.
There would be
It's
diagrams
possible.
connecting them.
Right? That things that looked orthogonal would have non-zero eigenvalues. Now it's possible, but as Sandeep says, sounds like a huge conspiracy that this matrix element would cut down the Hilbert space so much. Naively, you think that it would just, give you some off-diagonal elements. Right. So this is what I was wondering.
So one thing I should say about these models is that these kind of ideas were analyzed by Coleman a long time back, and there he was working in an approximation where you didn't see that cut down. So there it was literally not making a difference. There were some elements that were here and there and so on, but it didn't drastically reduce the rank of the matrix. Here, because there was a lot of control on these models, like you didn't need to do perturbative expansion, you could just do it exactly. It was important that you had to consider things like order e to the s naught number of universes and so on, and then you would see this cut down. So it's almost a doubly non-perturbative thing that you have to look for. Like in string perturbation theory, you would have to look for n-point functions of these gravitons, which would be where n is scaling like exponential in the G string, one of the G string or something.
That suggests that it's a kind of norm in string theory. This S naught I'm thinking is the genus count.
Is the genus count
parameter. So doesn't it suggest that it's some cut down you would see, which is kind of non-perturbative in string theory?
Yeah.
Whereas decays will start showing up just
That's
as
right.
Isn't it?
Yeah, that's
perturbation theory.
Yeah.
But then I don't understand. What is the physical expectation in that model?
One comment. So here, one way perhaps to understand this is the inner product. You can also think of it as an evolution, right?
Yeah,
let's say
Euclidean evolution.
Some evolution with the Hamilton. So then these true states are in some sense the ideal states of that Hamilton. And now it's an interactive Hamilton as opposed to free Hamilton. So one can imagine that the states that you see, the true asymptotic states, the ones that are appearing in the cut, which are alpha, are the ideal states of the true Hamiltonian, true interacting Hamiltonian string theory. And from that point of view, also you seem to land on gravitons.
But then you see that just in perturbation theory.
In perturbation theory only, in perturbation theory it seems.
Well, if you think about it as a Hamiltonian, then it's just some. Yeah, I guess if you think of it as Euclidean evolution, it can kill off some states, for example.
Yeah, point is a great point, right? I mean, if you start with some state and it just stays there, then those are the guys that are orthonormal in your basis.
Yes.
And those are also the things that are evolving time in a good way. And the only thing that we expect for that is these gravitons, right? Yeah. Right. So this is what we expect then, even in perturbation theory, or not?
Perturbation theory in G string.
In G string.
Because Abhijit's argument is just can be done in perturbation.
If it splits, if you decay, then you see that in perturbation theory, and then you don't count them as different states.
But that part is not so clear to me, that don't count them as different states. But I think one of Abhijit's points is that those things where you start with some state and you end with the same state in your inner product, so that it's not connecting with anything else. Are also Hamiltonian states.
I mean, the thing that I don't understand, I can see where Pratik was coming from. He said it's not perturbative that. Let's say to zero order with interactions, you have the one universe, two universe, etc. And then I'm doing it in perturbation theory, right? And I get small overlaps because a single universe can branch into two. Now you don't expect in perturbation theory a sudden cut down in the dimensionality of the Hilbert space till you include many small effects. The usual argument, right? And therefore it becomes a e to the s naught kind of effect, right? I mean, I just don't see it mathematically that if you're starting with infinite dimension, how just a very small perturbation will suddenly reduce the rank. That's why.
Exactly.
I can sort of understand that argument, and it seems different, non-perturbative rather.
Yeah, certainly in this model, I'm not sure what it's going to end up being there, but certainly in this model, you really need to have control over like finite S naught, roughly speaking. Like you need full non-perturbative control, and that full resummation, etc., cuts down this number of states. I don't think you would ever see it in what you would call here perturbation theory. Like in the genus expansion.
Just to understand, G-string would be like to the minus S.
Yes.
So G-string be yeah. Because
Then am I wrong? Then
Each string is a universe. No, but it's a similar.
You're right. Then you need n of those.
Yeah. No, but I just want to. I'll shut up after this. But I mean, what this thing is inventing some new rules.
Yeah.
But there is one model of 2D gravity where we're pretty sure of the rules.
Yeah, have we ever thought about the Hilbert space of in this language? Like, it
the
feels
Hilbert
like a
space
natural language for
The
that.
space-time Hilbert space is what I'm thinking.
Yeah, full quantum, right?
Full quantum space-time Hilbert space. But we do believe that n gravitons are exact eigenstates.
Yeah.
And so we have a lot of physical intuition for the answer to that.
Yes.
And it would be very nice. I mean, if you're inventing some new rules,
Yes.
to test those new rules out against a system where you have independent physical intuition to the answer.
Yeah, I agree.
If you say something surprising, then we should have an independent physical interpretation of that, right? I mean, it feels to me like when you've got you're inventing something new and you have something older that's supposed to fit into that, you're duty bound to confront the two.
Yeah, I think as you're saying, like
New rule being what?
All the stuff.
it's
That's,
not that,
I mean, inner product, that kind of thing. Right? I mean,
it's not that
thinking
new,
about it as
like,
an inner product.
I guess you would define the inner product this way even in string theory, right?
Okay, but then the claim, for instance, that you get a lot of cut downs.
So that I think is new, and there it was really important that we had full control on that theory, including these non-perturbative effects, to see that. Even in JT gravity, it's kind of challenging to see. So I mean, I would guess that string theory is at least as
No,
hard
but
as
say there was a
JT gravity.
claim that there was a cut down.
Yes.
Then that is making
That would mean
a claim about
Yeah.
the physical system.
Yeah,
And
absolutely.
then we can assess that claim as to whether it's reasonable or not.
Okay,
Given
that's
that we
fair.
know a lot about the physical system.
That's fair.
We studied it for years. Right?
That's fair.
So, okay.
I mean, it's not, it's somewhat counter, right? Because you have to understand quantization of string field theory and like the Hilbert space of string field theory.
Yeah. So let's say the technicalities are non-trivial, but let's say that there is a claim that it has only one state. Suppose. And then we could say no, they can't. Okay. Let's say there was a claim that it was a smaller Hilbert space than multi-gravitons.
Right.
I would say that sounds ridiculous.
Yeah.
Okay. I just want to understand what is the claim here, even if you can't do it.
So
What do you expect from it?
Yeah, sure.
Yeah, I mean, this is just laying out the formalism to answer that question. I don't know what the expectation. I mean, I guess the fact that in certain 2D models there is this drastic cut down makes you wonder about that question in string theory, and then it should be answerable. But I don't know if there's an expectation for the answer itself.
So I mean, just to say the same connect maybe, if you allow me to say maybe the following, if you take an initial state of many gravitons, naively you might think it can have an arbitrarily big Hilbert space, but the Hilbert space is e to the s Bekenstein.
Yes.
That would be the
But I guess in that case you can have like arbitrarily high energies and so on, right? So here you need something that's putting you in a finite dimensional Hilbert space. Like here it is coming from the Bekenstein-Hawking entropy. But I guess in the graviton case, like if you
many gravitons far separated, they're fine, right?
Yeah, but let's say you somehow put a total energy cutoff or something.
Total energy cutoff? Yeah.
Then we expect that the Bekenstein-Hawking entropy will put some bound on it, right?
No, not in flat space.
Rare.
But not in flat space, that's right. No, let's say in AdS.
Okay, but I was talking about just string theory where we understand.
Okay,
Right? I mean,
yeah. No, but then I guess so what I'm saying is the amount of reduction and so on is not a universal prediction of this formalism. Like it really depends on the details of the theory.
What I meant was, okay, sorry.
Yeah.
If we take the space of initial data in classical GR, convert it into a space of initial gravitons, which collapse to form black holes, you might still think naively that it's an infinite dimensional Hilbert space or something. You have very far separated gravitons which can collapse. But the real sane answer is it.
Yes. Actually,
Maybe that would be the version.
Maybe we should talk about the case where it's AdS, right? There, what would you expect the answer to be? Like put some energy constraint.
I expect the field theory.
Right. And that, so it would be a cut down from the naive Fock space and so on, right?
Yeah, it would be a cut down from the naive Fock space, but the cut down you start, as you know, Anyway, we shall have this discussion later. But as you know, you have to go to energies parametrically larger than n squared.
Yes.
To start seeing a cut down from graviton Fock space.
Yes.
The energies of order n squared, graviton Fock space is smaller than the Becken-Stein.
Correct.
You get an enlargement first and then a cut down.
Correct. But I guess these sort of effects would only kick in when black holes are relevant. So that would be like you're at energies of order n squared, but with some highest energy that you're looking at, that's still some finite dimensional Hilbert space. And the naive Fock space that you get from gravitons is cut down by the fact that there is a Bekenstein-Hawking entropy.
Yeah, it's very, very interesting. But what I mean is,
I agree with
something independently.
I'm suggesting that in fact the space-time Fock space of string theory has a cut down more dramatic than what Pratik is saying, because the decays occur just perturbatively. So the asymptotic states are.
Well, so the point about perturbation. So, I mean, it is indeed true that if you just have small corrections, the rank will not change. But it is in the same sense, right? So if you have, let's say, a cross off-diagonal matrix element for a massive state and two graviton states, right? But that still we can diagonalize and get an eigenstate which is a linear combination of a massive state, and so it will not cut down the state.
Yeah.
So in that sense, so what is really being seen here is not necessarily due to this decay of the asymptotic state perspective, but as a full, I guess, the full quantum theory, it could be far separated.
This is what I was saying, that the notion of asymptotic states in space-time could be a different notion, because you have very long to go in space-time. So here you might be talking to somebody. Okay, I don't know we should go on, but that's exactly the point. That the space-time notion.
Sorry.
Can you, in the last lecture, you said, what was the origin of the null state? Like, how did the.
So we just defined this inner product and then we look for states. So the set of states we considered was this. Among these states, I just have to evaluate the inner product on all states and check. Firstly, there was an assumption we made, which was reflection positivity, which was to say that the path integral is such that the inner product is positive semi-definite. Among those, you could have states which are of norm 0. And then you have to quotient by those because those are null states. So it depends on the path integral whether such states come up or not. So you just compute, given this set of states, look for things which have 0 norm and remove them from the thing.
And this statement is not matching with string theory. Is that the thing?
I guess it's a question of how much that reduction is. How many null states are removed when you do that. So there's some naive set of states that we had here, which you can roughly think as the Fock space, I guess. And then when you do this thing and look for inner products being 0, there'll be some complicated combinations which end up being null states. The question is how many of those null states are there? And that's a theory dependent thing. Like it depends on the definition of this path integral. Like in JT gravity, the answer is different. In Marolf-Maxfield is different. String theory is probably also different.
So one more question. In this new Hilbert space, can we talk about the entanglement entropy? And
we will talk about that. So we haven't gotten to any open universes yet. Then we'll be able to talk about it. So right now we're just talking about the closed universe concept.
In comparison to this universe with many asymptotic boundaries, comparing with the string bullshit.
Yes.
Is there an analog of the loop level string bullshit?
Yeah. So when we're summing over geometries here, we're really including all topologies and so on. So it does include all those diagrams, right? Because like imagine like we've defined the path integral like exactly. It really include all topologies, everything. So like disconnect, like there can be disconnections between these. There can be diagrams with holes and so everything. So it includes all.
What is the definition of Marolf-Maxfield model?
Oh, the definition of Marolf-Maxfield model is just like the action is the Euler character.
Just that.
That's it. Yeah. With some boundary. But yeah. Basically just the topological model. It's like JT gravity without the Diller complex.
I see.
Or the string without any action. Yeah.
Oh, that's
it's just
JT without the Diller.
Without the Diller.
So it just counts topology.
It just counts topology. That's it. Okay. Very good. So here, now we've arrived at some meaning for the path integral. Depending on the path integral, the set of alpha could be very different, as we just said. But in either case, what we're going to say here is that the way to interpret it. So we saw that alpha was labeling closed universes in the bulk. It's defining some state of the set of closed universes in the bulk. But if we try to think about it more from a AdS CFT perspective, This is a very strange equation because normally in a CFT, Z is just a number, right? So here we're interpreting this Z of J operator as an operator, which is non-standard in AdS CFT. In AdS CFT, if we inserted this, we would just do the path integral, you compute some number. So this is an extension of that, and then now the natural way to interpret it is whenever this outputs a number, those eigenvalues are related to definite CFTs. So each alpha is also secretly labeling from the holographic perspective, from the boundary perspective, a fixed CFT with fixed couplings and so on. So it's a definite CFT. And then the set of alpha would be some sort of ensemble of CFTs that are being averaged over when doing this path integral, if that's what's going on.
Alpha is the number.
No, it's a very general label. Like, so here, there could be many states that you're left over with. And so it'll label, for example, in JT gravity, alpha will label the entire Hamiltonian of the boundary theory. So there, the integral is really over all possible Hamiltonians of the boundary theory, and that's a continuous set. Alpha will label that. So it's here I'm just putting one number to represent all of that.
With a conformal.
Sorry?
With a conformal dimension.
Yeah, I mean, in a CFT, it would represent like the CFT data.
Can I just ask one thing?
Yeah.
Because, so let's say we were working in, anyway, we were working in one CFT or one Hamiltonian. So then the Z of J for any J just becomes a number.
Yes.
Z alpha of J.
Yes.
And does that mean that so now I'm fixed with that number,
Yes.
given a alpha and given a J.
Yes.
And now it doesn't matter whether that particular J is inserted with 5 other J's,
Right.
4 other J's to get the net amplitude.
It's always just a
the
number.
product of these numbers.
Yeah.
But the path integral may care, no?
That's exactly what so as you said, like, this is the factorization problem. As you said, like, I mean, if you had solved the factorization problem, if you were in a definite alpha, then if you had a 2-boundary partition function you were computing, there are contributions which include connected contributions and so on. But since everything is just a number, this should be the same as just computing the partition function there, right? Like just the product of those things. So somehow all of these things have to cancel out if that was the case in some smarts.
Sorry, this CFT is the statement that when you take this ensemble of theory, the problem of factorization is not itself there, but it's there, but
the ensemble makes you face that. So from the bulk we define some Hilbert space, and that's all fine. So we define some Hilbert space which may have some null states or may not, or whatever. Something. The puzzle is really when we try to face that with the boundary description. There, the factorization puzzle is really a puzzle because we don't know how to interpret the fact that there are these connected contributions from the boundary perspective. From the boundary perspective, we're just computing the product of partition functions. So why doesn't it factorize? It should have factorized if it was just a definite CFT. That is the puzzle.
No, but when you're taking these ensemble of CFTs,
Yes.
Is the paradox like still there, or are you?
No, if there's an ensemble, then there's no paradox. It's only a paradox if it's a definite CFT. Right? Like, I mean, if there was really an ensemble, like in JT gravity, for example, if there's really an ensemble, then there isn't any paradox with having these connected contributions because you're computing averages over this ensemble, and the average of a product doesn't need to be the same as product of averages. So there isn't a puzzle there. In JT gravity, you could still imagine going to an alpha state. So an alpha state would be one which is a definite Hamiltonian. We don't really know what the bulk description of those kind of theories are, like when we work with this. But if you were powerful enough to construct some path integral description of them, it must be such that the path integral factorizes. So that sort of has to be there by construction. We just don't have such a model where we know how that works. There's like very, very toy models, like even dumber than JT gravity where that happens, but we don't have any concrete place where we understand how that happens.
Sorry, can you again repeat what is the statement of the puzzle?
So we saw here that alpha was labeling the closed set of closed universes and fixed and the set of CFTs. Now in AdS CFT, usually or just I guess CFT lower is usually that CFTs are pretty rare. So usually think that there's a single CFT that's dual to this bulk theory. So alpha then would be just one thing, like there's no label really, there's only one thing. But then it's also labeling the set of closed universes, in which case you would say that the dimension of the set of closed universes is also one dimensional. There's no two different closed universes you can write down. Vice versa, if you say naturally there should be different states of closed universes, then you would have to somehow make sense of the set of CFTs that you're labeling with the same alpha. That's one way of saying.
Sir, how does one tie this to the fact that alpha is some superposition of these closed universes, and also it is a CFT? How does one
make that connection?
Yeah, make that.
It's because of this equation. Like we just want something where we want to interpret the number that's being computed by the CFT by those same boundary conditions. So it must, I mean, that won't happen in all states. It must happen in a certain set of states, and those are the alpha states. It's giving you some number there which you're interpreting as something.
From the bulk gravity point of view, when you are doing this bulk gravitational path integral, how are you arriving at this one symbol of CFTs from the boundary?
No, I'm not arriving at it. I mean, if I knew, I would have solved the problem. But like, we don't know what this ensemble of CFTs possibly is, but it's putative at this point because we're just defining the bulk theory first. There are these connected contributions that we're including, and generically that doesn't factorize unless there's some cancellations and so on. So generically, I will arrive at a Hilbert space which is not one-dimensional, which would then mean that there must be non-trivially different CFTs that I'm averaging over.
Finally, you are getting this integral over this alpha, right?
Yes.
Can we say something from the gravitational path integral? How are we getting this d alpha?
At this point, it was just abstract. Like there was, we just said that we don't know what the full set of alpha is. It depends very sensitively on what the bulk theory is. But no matter what the bulk theory is, I can always simultaneously diagonalize z hat and find its eigenstates. And that's what's labeling alpha. It will depend very sensitively on the theory, what these labels are, what these states are, etc. So I can't give you a universal answer for that question.
But let's say you have fixed a theory in the bulk. Then
fixed a theory means like a path integral or something?
Yeah.
Yes.
Then is there a description of getting this integral?
No, because even for a fixed theory like JT gravity, there's some answer to this question of what are the alphas. In Marolf-Maxfield, there's a different answer to that set, like what are the set of alpha. So without having the detailed theory, it's hard to tell you a priori what alpha is. It could be that there just isn't alpha, there's just one thing, like there's just one state. So it's really hard to tell a priori unless you have a concrete definition of the path. So this is positing, at this point we're abstract, right? So we're not saying what the specific definition of the path integral is, we're saying, give me a path integral which defines an inner product with this reflection positivity property. I give you a Hilbert space. What that Hilbert space ends up being depends on what you give me.
And since we are trying to contrast with AdS CFT, what would that Z hat of J be in normal AdS CFT?
Well, in normal AdS CFT, this thing is just a number itself. Like in normal AdS CFT, we would think there's only one alpha. So here, instead of alpha, I could have just labeled it with the Harlan-Hawking state.
Okay.
So I just insert, in the empty state, I just insert one boundary. That just computes a number. So this thing is just a C number.
It's just a boundary condition that you...
Yeah, this is just a boundary condition with source J.
Yeah.
And we just fill that in, get some number out of it.
Yeah.
This thing is not even an operator. There's just a C number.
So now we are trying to interpret alpha as the states in the holographic of this closed universe bulk.
Yes, but I just want to distinguish between states in the holographic dual in the sense of if we talk about open universes, then we talk about states in the CFT. And here we're being more meta. We're talking about like a set of CFTs and it's some state living in that more meta space. It's not the states in a given CFT. That's all I wanted to say. Okay.
In the JTD settled the external correspondence.
Yes.
So basically the ensemble average what you were
Yes.
saying about, it's given with respect to this rho of n, which is the coefficient function in the wave function. So the density of states is given by the
Yes.
coefficient function in the wave function by the wave function equals to partition. Okay. So
Okay.
basically when you take about there is the ensemble is defined by this density of state.
I would have said the ensemble is defined by the ensemble of couplings, like whatever is the boundary set of coupling. That has some spectrum and that gives you this, like the rho of E is like one example of one thing in that.
But when you are saying that, okay, I will not take an ensemble, but a rho means a delta, let's say, then you are in a specific ensemble.
This rho that you're talking about is the energy spectrum? Or
something like density of states, maybe.
Yeah, I mean, it's like the rho of E in JD gravity.
Yes.
Yeah, it's not that. I mean, that rho of E, we think of it as a continuous function, right? Like it's some sinh square root E or whatever. That itself is an average over many different Hamiltonians. In any given Hamiltonian, rho is just a sum over delta functions. So if you pick rho to be that sum of delta functions, that's like picking one Hamiltonian, and that's like an alpha.
Okay. And
basically, so sorry, basically what Pratik is saying that, okay, we can map suitably J even in DS to the SSS matrix model, but if instead of that whole ensemble, you take one realization, then that's like a particular choice.
Yeah.
And then the P alphas are like summing over all
them with some weight.
And depending on the state, you sign up all the like that. Oh, that we can sure.
Good. So as I said, like just to reiterate, the factorization puzzle really is in standard AdS CFT. We don't think there's any set of alphas, there's just one thing, but then you would end up with a one-dimensional Hilbert space. So this is the lower behind saying that the Hilbert space of closed universes is one-dimensional.
Absolutely. So what you're saying that if you had a particular CFT?
Yeah, I mean, in normal AdS CFT, like let's say n equals 4, we would think there's no alphas to average over. It's just a given fixed CFT. And then you're left with just a one-dimensional Hilbert space for closed universes. So define this.
So this is the lower behind saying that. Okay,
Yeah.
got it.
I mean, there's other type of arguments people make. I think this is basically it.
So sorry, but since you build on this, I think, so the idea is you take, say, n equals 4 super young mills, and now usually I think of it as some bulk and there's one boundary, or okay, I can have thermophile double and so on.
Yes.
But now you're thinking of, say, that plus a closed universe. Is it?
No, I haven't even got to that. Now I'm thinking about only the closed universe. So in n equals 4, we can build
to me. Like,
so in n equals 4, we can build solutions like, and let's not say n equals 4. In the bulk dual of n equals 4, like at least the low energy effective action of it, we can build solutions like that. And we're cutting it over in the middle. N equals 4 isn't being cut through. So it's not a state in n equals 4. It's a state of whatever that theory. So now we want to make sense of those kind of states.
but you can take the bulk
Yes.
2D dimensionally, whatever, low energy
Yeah.
limit,
Yeah.
and construct a path integral like that.
No, not just a path integral, we will talk about solutions.
Okay, it's good. That will be interesting.
Yeah.
You said it again and again, but just but in this kind of path integral,
Yes.
you did have what boundaries you were putting. You could take n equals 4 and turn on operators.
Yes. J is like that.
Yeah. So why isn't it affecting the states that you get in the middle?
Why isn't it?
Yes, you said.
So here's a stupid way of saying it, which is if you had really solved the factorization problem, then
there wasn't such a job.
Yeah, then this equals this and there is nothing there.
Yeah.
So it's the hard locking state. That's a stupid way of saying it.
Yeah.
But seeing that is hard. Like from the bulk, we have no idea how to see that. Okay. Let me just make a brief comment about this. There's one thing I've heard being said, which I might try to convey to you, which is that there's this thing called the Bekenstein bound, right? So Bekenstein bound puts a bound on how much entropy you can have in a region given the area of the boundary of that region. So you have some region with area A, then roughly speaking, the best thing you can do is fit a black hole there. So the entropy is always given by A over 4G of that region. Now, this was initially thought of as the holographic bound and how gravity imposes something like that, where it's a reduction of the number of states you might think you have in QFT. But this on its own is pretty drastic. And this is basically the same as the thing we're saying here. Because, for example, you can have a gigantic universe. So imagine something like De Sitter, we have a huge sphere, and we only look at some tiny region of it, right? here it makes sense for me to say the area of this surface is something and the entropy inside it is bounded by A over 4G, which is just the boundary length. But there's nothing special about this side, right? I could have equally well just drawn this side and said there's a tiny circle which bounds this whole region. And again, naively applying the holographic bound, I would say that the entropy of that huge region is bounded by A over 4G of this side. Taking the limit of this thing going to a vanishing thing, you would just say the entropy is 0. This is basically what's happening. Right? So this is one way of saying why we're ending up with this like it's literally like most of these island calculations and so on essentially boil down to this fact that you end up with a Hilbert space that has a dimension e to the A over 4G, where the A over 4G is the size of the throat that you like the thing that's got excised.
But how well do we know this?
No. I'm just telling you how to make sense of it. I'm not saying this is the correct way. Yeah. So I'm just saying how people thought about it back then and why we should not immediately say this. So
For extremal surfaces, I guess I can believe this. But
Well, even
there
that
you will
is-
shrink and then collapse, right? So it's not extreme.
yeah, but even that I'm not sure because so this thing was discussed a lot and at least 3 islands, the version that satisfied me and maybe some others was a concrete version of the holographic bound. It's what's called the covariant entropy bound, it's the Busso bound.
Yeah.
And the Busso bound basically says, if I look at any space-time, let's say in cosmology or something like that, if I look at any surface, what I'm supposed to look at are the light sheets of this surface, which is the directions in which the area is actually shrinking. So in cosmology, for example, that can be going towards the past. And so even in a black hole, you would say something similar in a black hole. Let's say it's an evaporating black hole. If you look at really late times, this is a tiny area. And naively, there's a huge amount of space here to fit in a lot of entropy. Right? So this would be a naive violation of the holographic bound because there's a large set of states you can have in QFT, but we're claiming, like the naive holographic bound would claim a bound on that. In this case, however, again, just like in cosmology, the 2 light sheets are these ones forward to right? This one and this one. And it's start off by a singularity. So there's a tiny amount of area really there, like there's a tiny volume there. And really, there's no contradiction between having that entropy being bounded by A over 4G. So this, in some sense, was a better version of the holographic bound, which made sense. Like it was consistent with standard QFT.
And just to say, sorry, you said it, but the total amount of entropy crossing these light sheets, as Busso defined it, is bounded by the area of the that origin from the sheet.
Yes.
Right.
Yes. Correct.
Yeah, it seems to be a
It
reason
seems
you
like
applied in various contexts. It seems, of course, there's no proof, but
Right.
okay.
But it seems like a much more reasonable version of a holographic bound, unlike the Bekenstein bound. However, many of the islands calculations, in the islands calculations, the things that we're finding are more consistent with the holographic bound interpreted as it is. The calculations lead you to that. And the Busso bound actually doesn't show up anywhere. Like it seems surprising to me that we haven't seen any indication of anything like a Busso bound in any of these islands calculations. They're right in the place where you should see them, but you don't see it.
I see. I didn't realize this. So you can do, and I'm sure you'll describe island calculations in those contexts, and it really seems to say.
It's simple. This is this one, right? In this case, you can do an islands calculation. And what the islands calculation is going to tell you is that the entropy of this whole region, which is the whole island, is bounded by this area. And that's very unlike the Busso bound.
Just to notice, is this the same island calculation we talked about the other day of Strominger and so on? Is that what you have?
Yeah, if you have flat space, then but you can do this in AdS or what. It's pretty generic. So even in AdS, you would find something like that, and it's same physics works.
So if this entropy means entanglement.
Good. It wasn't so clear. I think in the way Bekenstein originally visualized it, I think it was a coarse grade, like a thermodynamic entropy. So then the best thing you can do is fit a black hole with that amount of entropy. I think here also you would call it a thermodynamic entropy. But yeah, I don't know.
We don't quite know how to define such things.
That's right.
Yeah. That's in the gravitational theory.
But this is more
for general surfaces.
Yeah, this is we're imagining that we're working in some EFT limit where we're just talking about the QFT entropy strictly speaking is infinite, but needs to be regulated in some way. That QFT entropy being bounded by this A over 4G because the second law of thermodynamics has to hold. So the best thing you can really do is have a plan.
I never studied this paper, but Malvasena, Raphael, and so on have the quantum. So
yeah, that's like a version of this where you try to prove that. Yeah, in QFT they tried to, like in weak QFT they basically proved that sort of statement. Yeah. But in any of these non-perturbative calculation doesn't seem to show up at all. And something more like this shows up, and that's why we're led to this conclusion of, I mean, this is one way to see why we're led to this conclusion of one-dimensional Hilbert space, and it's as unreasonable as we would have thought then. So that's why we should learn about.
So just a tangential question. Like, what sort of principle does one, would lead to a proof of this type of statements that the entropy is bounded?
That the entropy is bounded
by the amount crossing the right sheet.
Yeah, very just.
So you mean this quantum books about that?
Yeah.
Oh, there they basically showed something like they looked at some light sheets and they integrated the QFT entropy on that light sheet. They basically showed that entropy was less than equal to the difference in areas here. Like this is say A1 and A2. There will be A2 minus A1 minus A2. How they show this? Yeah, so one calculation of theirs is just in free fields. Okay, in free fields, you just literally like brute force do it. And in interacting, it's like even worse because there what they end up proving is
actually kind of calculate in some more.
Yeah, in free field they like literally calculate.
Right?
Yeah,
Prove, right?
Yeah, it's literally like compute correlation functions in free fields and check that is check.
Sorry,
I mean, check as in, I mean, it's like in free fields, you know what the full set of states is, so you can just do it for an arbitrary state and do it. There's some argument for that. And in interacting, it's even less satisfying. Like in interacting, by their definition of entropy, the entropy on this thing is just zero. Because there's no non-trivial QFT operators on a codimension one slice, on a null slice, in an interacting theory. So it's not too satisfying to me, but that's all.
Might imagine that something like Cassini has this proof, right? Just in QFT, where he shows that the entropy about the vacuum is lower bounded by the modular energy. It's just follows from positivity of energy.
Yeah, it's that kind of proof.
Yeah.
But there, like in an interacting theory, they basically try to say that the algebra is trivial.
Yeah.
Like if you have some finite region, that thing happens because you have a semi-infinite region. So there you have a non-trivial algebra. But if you have a finite region, that is trivial. So it ends up being quite trivial that way. Okay, good. So let's just, before moving on, briefly talk about open universes in this context. So we talked about cutting through closed universes. We could have added also open universes to this thing. So we could have, for example, in the standard thermofield double, we could have things on this slice that we also cut through, right? And then this, as we usually define it, would be describing a state living on this Hilbert space of these boundaries. And that's the most standard version of AdS CFT when we talk about it. But now the only addition is, so this thing we can think of again as an insertion into the gravitational path integral of an operator we can call psi hat of fate. So there's some boundary conditions on this operator, and we're going to call it psi hat. And this operator basically would take some, so this psi has some Cauchy slice sigma that's living on these endpoints, and it basically takes the Hilbert space of the CFT on sigma bar to the Hilbert space on sigma bar union sigma. So basically just adds in one open universe with boundary sigma. You can define states there. So normally we just talk about the empty version of this where it defines a state on the 8 sigma, but of course we can add many boundaries and so on. So this will be, this just defines a state in that Hilbert space.
And then you would continue both endpoints, say to Lorentzian space, and you get
so
boundaries of AdS.
Correct. So when you cut it open here and then analytically continue to Lorentzian, you'd find a Lorentzian space.
So this is a feature.
Yeah.
So what is this? How is it doing H sigma bar to H sigma bar union sigma?
So for example, like let's say let's say I already had this
Your boundaries are just some, we are denoting them as points on the closed.
In 2D, it would be that. In higher dimensions, it would be connected. Like, for
But
example, it would be
it's not quite a boundary. You have to erase one part of it for it to be a boundary.
which
So it's like a defect, codimension one defect. You are not distinguishing between codimension one defects and boundary.
No, I didn't understand that one. I mean, if I think
You have
about
word on this side also on this side, right? That's why.
so I'm only defining the state here. So I'm splitting it here. Okay, that's what you mean. Yeah. I'm splitting it here to define a state, just like we usually do. So this defines a state. This is a ket. This is the bra, and this thing is like taking the
This
overlap.
itself is a cross section here.
Which one? This one.
Yeah.
This is like what you would usually call the bulk Cauchy slice, right? The thing that goes through in the bulk.
Yes. Oh, I see. It's just as this. It's okay.
Maybe that the thing on top was confusing you. Like
Okay.
So think about psi as just inserting a semicircle, like just a semicircle that I'm cutting.
Yeah.
So then it defines some state with the boundaries given by whatever is on the end.
So and then why is it that map then?
So let's say I started with this. So now I already have some sigma, which is these 2 points. I can act with psi hat and it will create 2 points. So for any sigma bar, the psi hat operator is going to
Sigma
add
bar
in
is a
sigma.
complex conjugation or
No.
Oh, I see.
The rest of
Tilde, whatever.
Okay.
Like any other set of sigma, all it does is adds in one more sigma. That's what.
Sorry, Pratik, I should have asked you, and you sort of alluded to it, but just the closed universes, these diagrams you're drawing.
Yeah.
I was thinking of them as, say, Euclidean path integrals or.
Yes.
But if you cut it, you get a state which you can also think of in the Lorentzian AdS theory.
Yes.
You're saying you can actually construct solutions.
Yes.
Like you do have closed universe in
Yes.
branching, etc.
Exactly.
So they match to.
Yes. Yeah, sir.
So I did not understand. So that is supposed to be filled, that semicircle is supposed to.
No, okay, let me erase this. Let me come on. So initially what we did was define some boundary conditions. So we had some slice on which we're defining a state, right? So for the closed universes, what we did was we added these boundaries. Maybe I'll use a color. So we added all these closed boundaries in the Euclidean past, some set of them. Now all I'm doing is to that set adding in some open boundaries. So open boundaries just means they go through this thing. So it's, for example, a semicircle of that type. That will define some state here. And that's all I'm adding. So this is like, if you forget about these closed boundaries, this is the standard thing we do in AdS CFT, right? Like if you imagine the thermofield double, this is just constructing the thermofield double state.
Right, but you could just add a strip there, right? Just like blue circles draw a blue line with a horizontal line.
Sorry.
Why are you just drawing it there? I mean, it's an initial state.
Oh, to cut it here? I could do that.
You could just draw like an interval there and then it will evolve like this with these.
Yes, I'm just trying to say that I can do both. I just want to distinguish. I mean, normally in AdS CFT, we just do this. And saying in addition to that, we could have added these things.
Yeah, but it's not clear to me that would be the thermofield double state.
Well, it has to be because these z hats, at least in higher dimensions, if we believe that there's only one alpha, these are just numbers.
And what is your point, Abhijit? So the yellow
Like, I
is
think-
how we think of thermofield.
Yeah, but I think if you add in this
You are
extra
just doing
stuff,
like that.
that's not the thermofield.
And then, you would have this kind of boundaries, right?
But that's already being done here. So I think your objection was why add these things.
No, I mean, then, in general, it would be like some. Yeah, I mean, it will be like some sort of a. Sorry. It will be like a strip cut off, right? Like that. So this is in general, it would be an integral of this sort, right? Where you have a closed universe and open universe.
Yes. But what's the difference with this? It's the same.
Well, I'm just drawing everything in this here.
How does it matter? Like, I mean, this is going to be in the Euclidean past. Your slice is not going through this.
Yeah, slice will be here, and
Yeah.
here it would look like this. Right?
You're saying in between it, you don't have.
Like, this is like a end of the world brain or something? What is this thing?
That's what I'm saying. So just the way you added a closed universe,
It's a boundary
open universe,
It's not an asymptotic boundary.
No, he wants it to be a boundary.
Oh, like the end of the world brain or something.
No, he wants it to be a boundary.
But then it's this. Then I don't see what's the difference with this. Like, what is this part and what is this part?
I mean, this is the open.
That is the asymptotic boundary.
That is the asymptotic boundary. This is not asymptotic.
So it's not some bulk Cauchy space.
That's your evolution, whatever that inner product has to do.
But this is some finite boundary.
Yeah, no,
it's like
not finite. I mean, it's still asymptotic. This would have
But then it's the same as this. What's the difference?
Not sure. That's what I was saying. I was not sure.
No, but maybe the difference for Abhijit is that if you slice this and you look at the space-time, it looks like one bit and then a disconnect. Or
Yeah. I mean, these can connect in the
I mean, so that picture would be like this. That's this disconnect. So this will go itself like that, and this will go like this, and then here when you have this cut, it would look like a this cut. So that is fine, but
And then
it's not clear to me that the state on this is the thermophile state.
Yeah, so that is a different objection though. That's an objection about this part, right? Like that's normally the thermophile double is defined just by this. Right?
Yeah.
And then your objection is if I add this stuff, is it still the thermophile?
Because I want to do the same kind of things that you were doing. That's why I did that. I mean,
that makes sense. And I'm saying your question is just that, right? Like if I add all of this, can I still call it thermophile double? And that's a reasonable point. But I'm just saying it's
no, when I have this boundary to be an open boundary like that. Or asymptotic boundary.
This is
the
an
open
boundary.
universe. No, starting from asymptotics.
This is that.
Yeah, I'm not sure why that is that.
I mean, this is some asymptotic boundary with open ends, which I can evolve to this Lorentzian thing.
But this is different, right? The thing that I do.
Maybe you can just draw the yellow lines in our basic section.
Yeah, I mean the yellow lines are here.
No.
They're the
Yellow line
semicircle.
is semi-circle.
Yeah, but this is a slice, and this is the yellow line. If I understand this picture correctly.
Yeah.
Those two lines are more like bulk Cauchy slices, which are connecting up to.
Yeah, this stuff is after you draw the bulk. Right now, I will draw this bulk.
Even this line here. They're like that.
That's why I was asking: is it an asymptotic boundary or not? If it's an asymptotic boundary, then it's part of the yellow line.
Yeah, I agree.
Okay.
I thought he said no. But
Yeah, I mean it depends on what it is. Like if it's a finite boundary, then it's not. If it is an
asymptotic boundary of the full manifold, this d-dimensional manifold. Right?
this is not a closed universe.
No, I mean, so
This one
first
will be
going back to the closed discussion.
If it's a closed universe,
Let's talk about this two-dimensional. So the asymptotic boundary, by that you mean the Euclidean boundary that is asymptotic.
it's just this part. It's just the blue part. Like if I fill this in, this is all finite stuff, and then there's an infinite boundary right in the past.
Infinite boundary meaning it's infinite length as you go along that, right?
Matlab the metric really blows up here.
Yeah, as you go along this.
Yeah.
Yeah, it is of that type.
This one is.
Yeah, there's this.
This one is, but is this? I wasn't sure what you're trying to draw. Like if it is, then it's the same as the yellow line.
No, that is not. That is just the.
So it's like an end of the world brain then.
Yeah, maybe it's a.
I mean, because the geometry you get here is like a strip which ends on something. What is that thing? I mean, if it's an asymptotic boundary, then it's like the yellow thing. If it's a finite thing, then it's an end of the world brain.
Sorry, geometry that you get is ends on something.
Yeah, the ends on. I mean, whatever these lines were, this interval will end on those, right? Like, let's say we don't have any of this stuff.
Okay. Yeah, I think I need to understand this better, but keep going.
Let me just say that this is the standard thing we would use to define states in AdS CFT. Forget thermophile states in AdS CFT. So this would give you some state on the CFT. And all we're doing is now, in general, we have a non-trivial Hilbert space of closed universes. So I'm free to add whatever closed universe state I want to that.
So I was thinking that what might say is the following.
Yeah.
Take the yellow line,
Yeah.
the two endpoints you continue to Lorentzian space. So you get a two boundary situation.
Yeah.
Now there are also solutions in Lorentzian AdS which correspond to closed universes.
Yes.
You can imagine a kind of multiverse where you have that two boundary situation with its additional closed universe.
Yeah, but they need not be disconnected, for example. They can connect and so on.
Euclidean path integral may connect them.
Yes,
in the
yes.
solution.
Yes,
But
that's.
conceptually, if you say you're adding these, what do you mean? You might say, okay, in a multiverse sense, you're Thinking of the original with additional closed universes.
Yeah, I mean, maybe it's
Is that
useful.
reasonable?
That is what I mean. And maybe it's useful to talk about it in the strings language because we were doing that. So these would be like closed string states you created, and then these would be like open string states, I guess, right? Like that maybe how I would think if that's yeah. These would then be states with boundaries that you're creating. And
What would inner product of this when open and when closed that would look like?
no, it doesn't. That doesn't make sense. So let me talk about inner products right now. Yeah. Good. So right now we've just defined this operator that's just creating states. So now initially the states were living in the Hilbert space of closed universes. Now this is a different Hilbert space. This is a Hilbert space where you have an asymptotic boundary, some sigma. Right? Now we can take an inner product between states within the same Hilbert space. So we have to choose the same sigma. So if I find another operator, which is some other psi, so let me call this is psi of j, and let's call this psi of j tilde. Then this is the inner product between these two things would be defined by psi of j tilde, j. Psi of j and psi of j tilde glue together to form basically a closed boundary. So they're more like these blue surfaces.
Yeah.
Right? So there's some z that's defined by that. Let me call that z of j tilde j. It's the z that you get by gluing it together. And that's the inner product. So the inner product will basically be done as you expect by gluing these together and doing the path integral.
In usual AdS.
In usual, yeah. So the only difference from usual AdS CFT is with keeping track of these extra closed universes.
But these can't connect to.
They can connect to it. I mean, the bulk would instruct you to fill in everything. So it would include, for example, geometries like that, and they can be all sorts of things here. So it will have also disconnected Euclidean geometries and also connect things that connect to the open universe and so on. So everything is allowed to be integrated over. Now, again, just to go back to that point, like in traditional AdS CFT, we never keep track of these because these are just numbers, right? So these in a standard CFT would just be a number. It's just multiplying the thermofield double by some numbers. So who cares about that? So we just keep track of this thing. Those will just go into the normalization and we just keep track of this. If there is a non-trivial state, non-trivial Hilbert space of closed universes, then you need to keep track of what other boundaries you added. Because of course, as you said, they are allowed to connect to the original open universe and give you something different.
And I don't want to slow you down, but since JT is a useful thing for me to keep in mind.
Yes.
I understand asymptotic boundaries.
Yes.
You put in a trace of e to the minus beta h for that. But for a closed universe, say in the SSS matrix model, what would you if you wanted to dimly
construct, you want to construct a solution or a
just a
configuration?
Let's say configuration.
Yeah, so then you for a closed universe, you just introduce like a beta 1 and a beta 2. Then there's a cylinder connecting them.
I see, but I see. Okay.
So it's like this picture, right? So there's a beta 1 here, beta 2. There's some cylinder connecting them. You can cut it open in the middle. That defines some closed universe state.
And the asymptotic case then?
The asymptotic case is if in addition to those betas, I also have another beta here that I'm cutting through. So then I would just think about the bottom half as this ket. So that has a thermofield double plus the beta in the asymptotic past. That's some collective state of open and closed universes.
It's really just you're computing expectation values of multi-traces, but it's how you cut it in a sense, huh?
Yes. I mean, but that's, that's right. And there aren't that many J's in JT gravity, it's just beta. So that's all.
I understand.
Because as we said, like when you glue psi of J tilde with psi of J, you just end up with one Z of J and you just compute that. That gives you the.
So Pratik, you said that there is no element which connects the open universe to closed universe?
No, there are. I mean, you allow everything to connect.
No, I mean a single open universe to a single closed.
In the inner product?
Yeah.
Yeah, I mean, this needs a boundary. I mean, you need
so using an end of the world plane. You should be able to connect an open universe to the closed universe.
The inner product is defined. So we have some sigma that lives on the psi of J, and we are defining H of sigma as the set of states we have with that boundary condition. So I'm only allowed to consider other psi's which have that sigma to even think of them as the same Hilbert space. The closed universe Hilbert space doesn't lie in that.
No, closed universe Hilbert space with the end of the word thing.
The end of the word thing. So you add some, but that would be a finite boundary.
Yeah.
Yeah, here we have an asymptotic boundary sigma.
Yeah, but finite boundary can connect to the boundary.
No, it has to be asymptotic somewhere. Like if I cut this out and I have some finite boundaries here.
Yeah, something like
Yeah, I want to define the inner product on this thing. So on this slice, it's never going to be able to glue to that, right? Like this endpoint will not glue to that infinite endpoint. I mean, just like, yeah. I mean, the kind of thing you're talking about is like if you have
There are super big.
yeah,
Right? Now this is closed, this is still closed.
Yeah.
Now you cut it here. Well explained. So now here you have asymptotic thing, right? And now so here you have asymptotic this thing. Now you just track this cross section.
no, so this calculation you're drawing is the bulk, right?
Yeah.
This thing you're drawing is the bulk.
Yes.
Yeah, so then I would say the thing you defined was it doesn't have this boundary at all.
End of the world thing.
But it doesn't have that boundary at all. It's not an end of like the only thing we're defining is this state and that state. Yeah. This is the ket and the bra is that thing. That's all. Everything else is filled in by the bulk. So this thing that you're drawing is a bulk thing. That's not a boundary condition at all.
Yeah, so bulk thing, but I'm saying this exists in the path integral.
Yeah, but even in order to get that, you needed the dashed line to match with the yellow. Okay, so we're always defining inner product between things that have the same boundary as asymptotic boundary conditions. Right? Like when you cut it open here, you generate like these two sets of asymptotic boundary conditions.
This Hilbert space of open universes are the subspace of Hilbert space of closed universe.
No, they're not. It's a completely different Hilbert space. Like, for example, I mean, in the simple example of JT gravity, the Hilbert space of closed universes is labeled by the choice of Hamiltonian, whereas the Hilbert space of the open universes is within one of those Hamiltonians, there's a full Hilbert space, right? Then all the energy eigenstates of that Hamiltonian. That's the set of states we're talking about in the open universe. Right, just like in standard AdS CFT, I mean, the Hilbert space that we cut through in the thermofield double describes like the energy eigenstates of that CFT. Whereas
from the open universes,
yes.
you are choosing one Hamiltonian and
no, not necessarily. Not necessarily. So we shouldn't talk about one. I'm just giving you a feeling for what that is. It's labeled by the set of states within a Hamiltonian. But of course, there's also the set of closed universes. So you have to label the Hamiltonian itself as well.
Actually, sorry, Pratik. I had a sort of question, I'm not sure it's the same, which is the reason why for the open case, you might say that, you have a lot of choice. Define this. I was thinking you can have various operators, that you could perturbations you could put on that boundary.
Yes.
And accordingly, the two endpoints will be in various states.
Yes.
But now, couldn't I do something like that, even an asymptotic boundary, closed universe? Like
I mean, in a general theory, there's a lot of sources you can write down. Like if you had JT gravity plus matter, for example, then you could add arbitrary matter sources. So it depends on what your theory is. There's going to be some set of sources you'll be able to add.
I see, but just in JT, you mean for the open boundary, there is a way to project onto eigenstates. Otherwise, I would have said, okay, again, the open boundary is really a full circle cut in half, and the full circle is just specified with the beta. So the open.
No, but you can try to compute, for example, when you cut through that, you can try to compute, say, the entanglement entropy of the right side with the left side, right? Yeah. In the end, those sort of calculations will become some path integral. As we said, any norm or any correlation function and so on that you compute will end up being some path integral. So you can always talk about it in terms of some Z. But it's just that we're defining the state psi and we can ask about some properties of the state psi. Whenever we calculate that, it'll end up being the gravitational path integral with some.
So it's set the beta of the above and below to be the same.
Yeah, you could, but you could have taken something else and it would be the inner product between two different states and so on.
I'm not sure I know how to compute it, but I'll ask you later.
No, but like for example, you could have like thermophile double at temperature beta and then thermophile double at temperature beta prime, and the overlap is just given by beta and beta prime, like beta O2 and beta prime O2.
You're trying to do that.
That just becomes like Z of some other beta, right? Beta plus beta prime O2.
So, thank you. If you talk about these solutions, I mean, not in the talk, but offline, where you have end of the world plane connecting the boundary slice. It is of that type, right? So this solution is.
That's right. And that defines a state in the same, the boundary condition for that is just the boundary condition that you have on the CFT. Everything else is filled in by the bar.
Yeah. Yeah. So it is of this type, right? Isn't it?
No.
Apple core kind of thing. Where you have this, and all that other such a thing was happening.
Yes.
And then there was this. Yes. This is the boundary state. This is the boundary. Right?
Yeah. So here
this you have the end of the world connecting to the particular boundary slice. So if you remove this, exactly what is happening here.
So let me just draw it. He was discussing it. So it's some geometry like that, right?
Yeah.
And all I'm saying is there we're defining a state on some slice like that. And the boundary condition for that is just this, where the yellow slice, the yellow part of this thing, right? This thing.
Yeah.
And that only has this boundary, like a circle here.
Yes.
And that's it. This thing doesn't count as a boundary for that.
No, I'm not talking about. I'm just talking about the rules. So
The
here
rules
you are
are
considering
including
geometries which allow for the end of the world plane to emanate from a boundary slice, right?
Yeah.
That's what is happening there. There is a boundary slice.
Yes, that's right. That depends on what boundary conditions you put here. So I'm just saying that in the yellow thing, you can have, so here the boundary conditions that you have will be some source for that end of the world plane. And then it can emanate from that. I was just trying to say that even here, like it's important that we glue the same sigma to the same sigma to define an inner product. Okay. The state here is still defined on a single circle, not on two circles. Once we fill in the bulk, then in the bulk we have two disks. One which is truncated by the end of the world plane and so on. But on the boundary, this is still a state of just one circle, even though there's a disconnected component. Okay. I mean, the only thing I'm saying is that this circle doesn't intersect the slice we care about. That's all I'm saying.
That's a matter of where you cut this picture, right?
Yeah.
Just as a fact, the rules, you are considering all geometries of this kind where end of the world
but it's a question about what your operator is. So the psi hat operator is, so first I fix some slice on which I'm defining these states, right? So there's some slice that we are cutting through, and then I insert whatever boundary condition is defining the state psi hat. That is this boundary condition. Given this slice, this is how it intersects that slice. It only intersects on one circle, so it defines the state in this Hilbert space of one circle. Just like we would in ADS.
This slice is the slice of closed universe Hilbert space.
Which
you are putting this, you are choosing a slice of a Hilbert space of closed universe.
This one is an open universe. So this one, it's going all the way out to infinity. It's an asymptotically AdS universe. But then as Abhijit drew this one is cut off by end of the world range and it's a finite region. So in this case, there's going to be closed universes floating around, but there's also in this case one asymptotic AdS universe, which is defined by this boundary condition that's fixed by psi. So the only thing I wanted to add using this open universes was just going back to the page curve calculation. So it wasn't really so important. So let me not get too much into it, but let me just say how this connects back to the page curve calculation. So if it was, using this construction, from the bulk, we see that there's some natural, non-trivial set of Hilbert's closed universe states that we find. There's some non-trivial Hilbert space. And now we can add in operators that define also open universes. So that can define states in what you would call the CFT, standard rules of AdS CFT. Okay. And so there we can try to do something like black hole evaporation. We can do black hole evaporation and construct some state. So remember, we had some picture like that. And we can define the state on this region. So here, all of this should be thought of as yellow stuff. This middle stuff is not defined as a boundary condition. It's something that we're getting by filling in the particle, but I'm drawing it because that's sort of the dominant contribution that we're going to find. There's going to be a bulk slice that's going through this. And we can do things like a page curve calculation where we try to compute the entropy of this region. In order to compute the entropy, we compute this what's called the swap test. So we take 2 copies of this thing and then swap them to compute the Renyi entropy, second Renyi entropy. And so that looks like this. Again, these are all yellow slices. This slice you can imagine going through the whole thing. It potentially has other closed universes and so on. We set this up, and then the state that we're going to find that comes out of this. So the density matrix on this region, let's call it A, is going to be given by, firstly, so just think about the process. So alpha here is labeling the couplings. For any given set of couplings, there's a particular black hole S matrix for any particular choice.
So, this is not an AdS CFT context anymore?
It doesn't, sorry, it's not so important that it's flat-based. We can be in AdS CFT.
Okay, so AdS coupled to Bath?
Yeah. We
can
be in AdS
plasma balls?
Plasma balls is fine.
Plasma balls. Okay.
Any concrete boundary condition I can set up, let's say in AdS plasma ball.
AdS plasma balls, okay. And now in the plasma ball context, what is your slice?
It's just so the slice is just cutting through,
going through part of the ball.
No, it's going to go through the whole thing, but I'm just going to compute different. So let me draw the plasma ball. So there it's going to look something like that. There's some black hole that was formed around 8-ish times. So there's some slice there. The slice just goes through all of this. Just going through the whole thing.
Okay.
And here we can pick a sub-region.
Sorry, this is the replicated, right?
I'm just taking 2 copies of that. 2 copies of plasma.
Yeah.
And what I'm going to try to do is take the sub-region of the plasma ball where all the radiation is getting collected and try to compute the trace rho squared for that.
Okay.
To see what's the Renyi. So now we can think about what the state is. So the state on that region will roughly will look like this. It's a direct sum over alpha of the following. It's some weights times Ci alpha. Yeah, it's I alpha. So let's interpret this statement. So this is the full density matrix in the full Hilbert space. The full Hilbert space here is the Hilbert space of both closed and open universes. Right? So we're defining some state which has this 2. So let's first just talk about the density matrix on one of these. So if I just had one of these, there's just a single density matrix of the CFT that I'm talking about. But it's important to keep track of the fact that there was also closed universe couplings that we were keeping track of, the alpha labels that we were keeping track of. The way to interpret it in the bulk would be roughly as coupling constants. So if I fix the choice of coupling constants, there's a definite S matrix that comes out. But that S matrix will sensitively depend on what the choice of couplings is. So for any given alpha, there's some weight P alpha, which we defined before. And there's some specific S matrix. So this part should think of as the S matrix. It's the S matrix, which is I'm sorry, there's a sum over Rng.
I'm so sorry.
Yes, go
on. They explained that so many times. But so here the alphas are the state of the various.
You can think of it as either the state.
Those alpha.
Yeah, it's the alpha eigenstates. It's the state of the closed universes, or equivalently the choice of CFT.
So, what is the closed universe in this context?
Yes.
So let's just talk about the CFT. So in the CFT, what we saw earlier was that the closed set of alpha was labeling both the state of closed universes and the CFTs that we were averaging over. Right? Okay. So let's forget about the closed universe part. Let's just think about it. It's more natural to think about it as the choice of CFT. In each CFT, there's this black hole evaporation process that's happening, and there's going to be some particular S matrix that spits out some state. That state here is very abstractly, I mean, I'm just writing some general coefficients. So if I fix an alpha, then I'll get some state which looks like this Ci alpha, Cj alpha star with some state of that type.
In every CFT, you have subregion. Like in every
CFT, I try to compute the entropy of a subregion. We can also do the full thing if you want, but whatever, like it doesn't matter. But in every CFT, we'll try to do that. But what that means is every CFT here is just labeled by alpha, right? So now what I'm saying is for every alpha, there's some S matrix that comes out. Those coefficients are just some general coefficients I've written down, but the important point to keep track of is that they depend on alpha. The specific S matrix will care about what this alpha is. Good. So now, from this, we can try to compute the entropy.
And the I and J are just state labels in
the Hawking radiation basis, whatever that is. So now in this thing, we want to compute trace rho square. Now the important thing is going to be a distinction between what does trace rho squared really mean. Okay? There's two different things we can try to compute, and they're going to give us different answers. So one thing you could have done was just trace out the alpha label. So suppose you didn't know anything about alpha, you were just an observer who was doing this experiment. You would trace out over alpha. When I trace out over alpha, this will end up being essentially sum over I, j. And with weight P alpha, we essentially average over the Ci alpha and Cj alpha star. So it's going to be an average of Ci alpha, Cj alpha star, I, j. This is now a quantity within a single CFT. So that average is with weight P alpha. Okay. Just to make it suggestive.
It's a quantity with it being, it's a density matrix of a single CFT.
Yes.
But you get it by averaging over various.
Correct. Yeah. Correct. Now, since you averaged over various things, this is just going to be, this is roughly what we call coarse graining, right? It's as if you didn't know what these details were, you just computed the average density matrix. And this thing is basically the density matrix Hawking computed. Right. So here, there was no reason for the state to be pure because we sort of lost the information of alpha. Alpha, the state was entangled with alpha. And so we end up with a mixed state after tracing out alpha. That state is going to have a large amount of entropy. And the answer you can show with calculations is just the same as what Hawking would have found. Roughly the way to think about it is it's just coarse graining over the details of the S matrix, as you don't know the exact S matrix.
Sorry, but I actually never sat down and thought about this very much. People would say, if in any one CFT information is not lost, then averaging over them also you use it.
Yes.
You get thought of that way different answer?
So it depends on what you're computing. So you could have computed. So this thing is like computing trace of average rho squared. This answer. On the other hand, of course, you could have computed average of trace rho squared. These are two different things we can compute, right?
And that's the second one is what?
The second one is what I have.
Yeah. So this thing gives you the Hawking curve. Because you've course grained over the fact, the unitarity of that S matrix is a very delicate thing. Once you average over these things, you basically lose that and you have a mixed state. This thing will keep growing. And so this is going to follow the Hawking curve. Whereas here, what you're doing is really computing it within each instance and then trying to see what the entropy is conditioned on that instance. This thing is going to give you a page curve. Because each CFT only has that many states. The place where the Hawking curve is coming from, this extra entanglement, is coming from the entanglement with all of this alpha. It's coming from the thing that you traced over, which is alpha. So that's the interpretation of the page curve calculation in this language. If it was that there were a non-trivial set of alpha, the way to interpret it would be to say that if you really traced over alpha, then you really lose information because the information was in the coupling constants. But if you measured all the coupling constants, if you conditioned on a particular alpha, then of course, a given CFT should be consistent only with that many number of states, and you should see the page curve come out of that.
Terribly sorry, but I'll have to beg off and leave, but please do continue. But I just want to say one thing. I'm calling you back. I just want to say one thing. This really suggests a connection also between where Hawking goes wrong and the the fact that the Hilbert space doesn't factorize, well, I'll talk to you later because when Hilbert spaces don't factorize in wave series, you get super selection sectors. Like it's a sum over different select.
Yes.
It suggests because here the sum over alpha is a bit like different super selection sectors.
That's right. That's right.
So it could be due to wormholes, but it could be due to various reasons. And as long as you have to sum over different sectors which never talk to each other and you're not careful.
Yeah, so let me just say that. So, I mean, here, the analog of that is that, I mean, suppose you only access asymptotic boundary observers, like you're in the CFT, then alpha is something that you can't really access, right? Similarly, in the gauge theory, these degrees of freedom that factorize the Hilbert space are something you can't really access as a low energy observer. Like, suppose it was that this was an emergent gauge theory. They exist in the UV, but they don't really exist in the IR, so you can't really access them, but nevertheless they're there and they contribute to the entropy depending on how you compute it. So it's similar in that sense.
Very interesting. Okay, so sorry.
Just a simple question. There are two ways that this trace of expectation value of lambda square.
Yes.
Is this just that in the first case you are first summing over alpha and then taking then over ij rather than first over ij and then alpha?
No.
So what was the formula for secant? Can you write down?
This thing? Oh, this is just computing sum over alpha, the alpha, trace of rho squared in alpha. So trace of rho squared would be just fix one of these labels. So fix alpha, then you get just this thing, compute trace rho squared for that density matrix. Basically fixing one particular alpha and just weight that whole thing by P alpha.
So is that product of numbers or is that really this product C alpha C alpha?
This one is a product.
So is that this product?
Sorry, which
C alpha C.
Yeah, I was meaning it as a product of two numbers. It need not be. I was thinking about really like at the end of evaporation, like when it's really a pure state. In general, it's some density matrix that covers.
So rho square average then trace it will be equal to this average of trace loss.
Rho squared
Then
average.
trace. Because there is a P alpha weightage, so
You're saying here
no, the page curve. Go to page curve.
Yeah.
These are the two options. Another option.
Yeah, I know. You mean like trace of average rho squared.
Exactly. This is equal to this average of trace loss.
No, I think in this case, this is also going to be more like this.
So in this range, you mean sum over alpha and by trace you mean sum over alpha, right?
Yes.
So they just become middle.
Yeah.
They're just two sums.
Yeah. Oh, sorry, here. So this is the same as this is what you're saying.
Yeah.
And this is the sum, sir.
So the picture, physical picture is that we are living in some ensemble given by some closed universes, right? Some closed universes, and then whatever is happening, it's just happening in that ensemble, that kind of.
Yeah, I mean, this is basically Coleman's picture. So this this is just a precise version of Coleman's picture, which was to say, suppose we have these wormhole effects in gravity that induces, I mean, then there are these, what that results in is uncertainty in the choice of couplings that we see as low energy observers. As low energy observers, we have some couplings in the standard model and so on. These wormhole effects lead to fluctuations in that. So it leads to an uncertainty in our choice of alpha. We don't know exactly what the couplings are, and it's some fundamental thing. That's sort of the picture. And then if that is the case, then what you find is, depending on what you measure, you can see either the Hawking curve or the page curve. The rebuttal to this is usually that we can just try to measure all the alpha. So if we just first do a lot of experiments to measure exactly what the couplings are, then do this experiment. Then of course we're now already conditioned on a particular alpha and we should see purity from that. Right?
But if I do something low-brow as measuring correlation function,
yes.
how do I cover the cluster decomposition?
Yeah, this will be a big violation. I mean, not a big, I mean, it will be a violation of cluster decomposition.
But in physics, we don't expect that, right?
Yeah, I mean, then you'd have to put bounds on it.
So that would depend on the thickness of
the thickness, like how precisely you've measured the couplings.
No, I mean this P alpha.
Yeah, that's how
No, I
precisely
don't
measured the
measure
couplings.
coupling at all.
Yeah, so then that.
Even then I recover carbon.
As you start measuring the couplings, that P alpha will shrink in width, and so it will depend on how sensitively you measure the coupling.
No, let's say I don't do any quantum gravity stuff when I'm measuring, my correlation function.
So from the gravitational path integral itself, you get some P alpha, and then it will be it will depend on that.
Just in quantum field theory, I want to measure for the standard model.
Yeah.
Right. So there I do expect cluster decomposition. Maybe it is violated by a small amount.
So that small amount will be controlled by this P alpha.
Yeah, exactly. So that will put that P alpha is very concentrated.
Yeah, it has to be. I mean, this P alpha is. I guess it depends on alpha, so it's not so.
No, I mean as a distribution. What is the P alpha as a distribution?
No, but I mean, if I knew what the set of alpha was, then I could say something about it. Like it could be a discrete set. It's not so clear what alpha is.
No, but whatever it is, it has to be sharply peaked for standard model correlation functions to be cluster decomposable, right?
So you're saying like
I need to be living in one CFT, almost one CFT, always.
It depends on how much the correlation functions care about that, right? Like when you're computing something like a 2-point function, and that itself could be a self-averaging thing, right? Like if all those choices of CFTs could give you almost the same answer. So it'll depend on the observable, how different they are. Like the thing that we measured here, like the Hawking curve, is one where you see big differences and so on. But if you're in a very low energy regime, so these alphas, of course, if in order to be consistent with the AdS CFT, they have to be consistent with low energy physics. They have to be consistent with the low energy EFT. So it has to be different completions of almost the same EFT. Okay. So that it's not that drastic. Otherwise, this like completely fails.
Different completions. So
it's like slightly different UV behavior, same IR behavior.
So is that an argument for, like alpha should be something very continuous parameter always, right?
It depends on the model. Like there are models where we know it's discrete, there are models where we know it's continuous.
And it's discrete in those models, do you see like different
Yeah. So I will say that the model where you see is discrete is this Marolf-Maxfield model, which really has no dynamics. So there's no like matter fields and so on. So there's nothing to ask about. JT gravity is a little better, where you can perhaps ask about the dilaton correlation function, etc. And there it already becomes continuous. So I guess you would expect that it's continuous. Yeah. I'm just laying out the scenario. Should we finish?
When I trace out over alpha, is it like target entanglement or like tracing out the?
No, I mean alpha doesn't have a very simple target space. If you think about it from the gravity perspective, it's really tracing out the state of all the closed universes, roughly speaking. Like here, maybe it's easiest to understand in the black hole case. In the black hole, the thing that Hawking did was he obtained some density matrix. How did he obtain that? He obtained it by tracing out the interior, right? That gave him some mixed state, and that gave him some non-trivial entropy. That is like alpha. So alpha here is really representing all of those interior degrees of freedom that you traced out to get a mixed state.
If we see from the one universe point of view, but if we are saying from the set of closed universe, then alpha labeled to every closed universe, and tracing over alpha, it means you are tracing over some closed universes.
Like the interior here is roughly like a closed universe, right? Because this thing, once it's completely evaporated, is basically like a closed universe. So there's a whole bunch of closed universes floating around, but there's also this one. You've traced out all of that. That other stuff is not very entangled with your radiation, but this one is. So it changes the answer much more than the other stuff. But yeah, you're tracing out all of it. So in this language, it's okay. Just to say, here, you could then ask, what if I fix the couplings and then try to do this calculation? There's no controlled model where we actually understand the bulk calculation in a fixed coupling instance. Now, there's two options then. You could say that, there's really one option. Since it has to recover the page curve, it must be that there's somehow secretly a pure state in your hand, right? And then we get back to all the questions that we discussed previously about how it's hard to recover the information in some semi-classical calculation. So presumably it comes at the cost of losing the interior. Once you project onto a definite alpha state, it presumably just completely ruins the interior and puts a firewall there or something like that. That would be what the scenario would be. And the only reason we've not seen that in any of the other calculations is because there's a non-trivial set of alpha, and we were doing the calculation in the Hutton-Hawking state. In the Hutton-Hawking state, there's no contradiction. You can have this Hawking curve going up forever and so on. We haven't conditioned on a particular alpha. So there's no contradiction with having a large amount of entanglement with the interior. But then once you condition on a particular alpha, you're back to the same sort of questions. But at least there's a consistent story for how the gravitational path integral calculation worked okay. The reason it worked okay was because we were doing the calculation in the Hutton-Hawking state and not in the alpha state. If one were powerful enough to do this calculation in an alpha state, presumably they'll see other effects which spoil the interior. That's sort of.
One more thing. Here you got a page curve, and in that picture you got a page curve by inserting this island.
Yeah.
So how this will?
No, it's the same. Like so, this page, this trace law squared calculation will end up being exactly like that. Like the way it will work using the bulk path integral is you will set up boundary conditions corresponding to trace rho squared. What does that mean? I'll take 2 of these copies and glue them cyclically and so on. Set up that as a boundary condition. And then this average, remember, was just do the path integral. So you do the path integral with those boundary conditions. The saddle point for that is the islands. So this calculation is really the same as the islands calculation. Okay.
Well, we're just going back to that picture that we were drawing with the end of the world brain.
Yeah.
We had a lot of discussion with string, the analogy with string theory. Right? In string theory, we know open strings can strings, right? So in that sense, I think this would require a little bit more setting up to do that out.
To rule that out?
Yeah, that there is no such process.
No, there is such a process. I mean, the process you drew, like the one where we just had this one open boundary and then we had some other thing propagating.
Yeah. I mean, I'm
that
saying
is one
the
such
matrix
process.
element from open to closed is non-zero.
Matrix element. What is the Hilbert space we're talking about?
So in string theory, when you want to define open string,
Yeah.
you would have to define it as a string on the plane, right?
Yeah.
So it would be a disk, and there's a mark point on the disk on the boundary of them. And then the closed string vertex operator is somewhere in the interior. So that will let you have a non-zero contribution.
No, I don't think that.
A matrix element for one closed string to 2 open strings will be non-zero. Closed string would have to be. F square can become T. Maybe that's relevant to this.
Yeah, I'm just trying to understand how you're gluing these things together. So you have some open string state and some closed string state.
Yeah.
Where are you gluing these things together? Like the closed string is defined on some finite circle. This has some boundary. Okay. Yeah. Not sure how you're.
If you cut like this, you get 2 states. 2 strings.
See, two strings. Just saying a disk with the one mark point on the boundary and another mark point in the interior.
So it is with one mark point in the interior
And one mark point on the boundary.
Okay.
Wouldn't that be non-zero?
Just this?
Yeah.
Where are you defining the state?
Those are the states. The mark points. And just the open strings on the D brain, it just becomes, pitches off and becomes closed string.
2 open strings. Trace F square couples to grab it up.
But just as a string word sheet, this should be there. Right?
I mean, I was thinking just like this, that if you've got a closed string, it can break up into 2 open strings. This thing does that.
But this, what about this?
Yeah, let me translate it.
So what is this? Where is the brain here?
Yeah.
That's the boundary condition.
Like this is the brain and it's like this.
No, this boundary condition is the brain. The open string boundary condition given by the field. That's an open string there. That's a closed string in the middle. With the way we were drawing these pictures, right?
Yeah.
all your ordisms. Like that. Right. These are asymptotic states. Yeah. Yes. Yeah.
I mean, you mean with these circle boundaries sort of? Yeah. Okay. Okay. And then you're cutting it not on those, right?
Let's say something like this.
Okay. Okay. But you're not cutting it on
This is how we were thinking, when you're talking about strings being
yes.
closed universe.
Yes.
But in worksheet, this more standard case study, this is the vertex operators.
Yeah, as long as we're careful about where we're cutting it, I'm fine. So here, as long as we're saying we're cutting it not at those asymptotic boundaries, then that defines the status closed universe strings.
There will be some closed string here, then some string here. Right, and this would be the end of the word vehicle. Deep braid will be the end of the word. You may say that your theory does not have deep brains, so there is no end of the world. But I don't know. I mean, if it does, it will have this one. I don't want to be relevant. It's a tangential point. I don't know whether it's going to be important.
Yeah, I think I don't understand.
So,
yeah.
Yeah, we can work for that.
I suppose you can have an open string closing up. That's the kind of thing that could happen. I mean, normally two open strings come and do this.
Yes.
Abhijit maybe is imagining.
Closing up. Yes, that's what I'm saying.
Yeah.
Just sliding, pinching out.
Yeah.
Oh, that's what you remember.
Yeah.
Closing off. Closing off, I would have thought as a limit of this thing, right? Like, I mean, I think that's similar to having this double like thing where you're taking these 2 points together.
No, maybe it is happening through this. This is the picture. This is the worksheet picture for that.
But can you draw a slice where we think about that as an inner product between? Yeah. Yes. But why is that a open string? I mean, maybe we're calling it different things, but in this language, this would be a state of closed universe. You're just cutting it on a boundary of finite values.
Yeah, sure. I mean, that's the intermediate state.
Yes.
But I'm saying as an external state. And then if you are computing matrix element between some state, that's the whole point. You were treating this whole thing as if there is this thing that closed universes do, and this is the thing that open universes do.
Yes.
And they don't do much together.
No, I didn't say they don't do much. I'm just saying they live in different.
I mean, it seems like they're not doing much, right, together. But I'm saying those Hilbert spaces are connected. Using this,
I mean, the whole point of what I'm going to say is the constructions where the closed universe and open universe do interact with each other.
No, you will probably get that, but so far, at least the impression that I was getting is that there is some P alpha that is describing some closed universe sector.
Yes.
Right, and then there was this open string, which is kind of an addition to that. They were not kind of playing together because these matrix elements were absent. But
the matrix elements can be there generally. I just mean
if they were there, then you would have to rediagonalize this thing.
No, I don't have to, because when I add this thing, I can add in all of these extra operators. So we started with some state alpha, right? And then we can add this psi hat operator. But firstly, psi hat commutes with all z's, right? So before and after, the eigenvalues of z don't change. So you don't have to rediagonalize it. It's still the same basis.
What about the number of null states?
No, it doesn't change either. And the reason is, if you had a null state, so null states basically were such that the overlap with any z state is 0, right? This thing is 0. Like for any choices of z. And even after acting with psi, the same. Once psi and z commute, then it's all the same. So you don't have to rediagonalize, and it's still the same set of states. It's just an extra layer. But I'm just trying to distinguish between.
Here you are using the fact that the inner product is vanishing between them. Between open and closed.
Yeah, I mean they're on different Hilbert spaces, so I don't know how to define an inner product between them. Like here in the language you were saying, the states you defined were in the Hilbert space of closed universe.
No, I mean, you could consider 3 closed universes here, 2 closed universes there, right?
Yes.
And then still have inner product.
Yes.
So
that's still in the
that
Hilbert space of closed universes.
Yeah, so now my Hilbert space is of closed and open universes.
So when you say that, I just mean that you can have an arbitrary number of boundaries here and arbitrary number of boundaries there. It just start in the middle, where there's open universes and closed universes. Yes. Yeah. So I was just saying that we can add all of these closed universes in the past, and then there can be some open universe boundary condition. And I'm just saying that this, before I added this operator, this was a state that lived, I mean, it can have all these connections and so on. Right? It just lived in the Hilbert space of closed universes.
Yeah.
In the sense, it just has some finite volume thing in the middle. On top of that, if I add an extra boundary with this, then the things that will fill it in will in particular be infinite volume because they have to go all the way out to this boundary. That's
but that's
So
why
the
I'm
different
saying that
Hilberts.
if you add end of the world brains,
Yes.
then you get a new, new type of selection sectors to that.
So
Where
this
you
end of the
have
world
end of
brain-
the world brains also.
end of the world that you're thinking of as some bulk boundary condition, right?
Bulk boundary. Exactly.
So here, only things that have been defined, all the operators that we define are asymptotic operators.
Yeah.
You could add extra operators to this thing and then define some different Hilbert space and so on. Right now, we're just talking, right now, the only things I included here were asymptotic boundary conditions, as you would in AdS CFT, where we just define asymptotic boundary conditions.
Yeah, but it
From
seems
a
like
bulk
this
theory
picture is
perspective-
begging for an extension of the
You add it,
bulk Hilbert space.
Yeah. I mean, so in the Marolf-Maxfield paper, they do add these end of the world brains. But there, the interpretation is, I mean, similar to what we talked about in the PSSY model, where you have some yellow thing, and there's some end of the world brain boundary condition. So that would have created an end of the world brain. You're cutting it here. You just think about that as a one-sided state in the CFT, just as you would in standard AdS CFT. This is just projecting onto some definite state. And it's still a one boundary state. So in that sense, it's still in the Hilbert space of open universes with one boundary. This is in the bulk, it's an extra boundary condition, but in terms of the asymptotic boundary conditions, it's just a source that you added in the past. It's no different from that. Okay. Yeah, I guess we should end there. But yeah, thanks.
So this part was just saying that you could do some averaging
Yes.
and get back Hawking state after some averaging. Well, that particular alpha didn't seem to play much of a role. In many ways.
So the role that it plays is by this connection that we discussed between the fact that alpha labels both the CFT and the set of closed universes. And the way we're interpreting it in the bulk is essentially what we would say in EFT, which is that the information is lost because it's in the interior, right? So we traced out over something in the bulk, which was the interior and other closed universes, as pointed out. That stuff is really there, like your Hilbert space, it's like real degrees of freedom in your Hilbert space. Since you traced out over that, it's natural that there was a non-trivial entropy.
I see.
But nevertheless, you can ask, okay, so what about the page curve? And the way to recover it is do a different thing where you first measure the couplings and then ask about this question, and then you find that.
Which is like measuring the state of that closed
Measuring the state of all the closed universes. Yeah, that's right. So you do enough experiments. There's a very, I don't know if I should say that. There's a very toy picture for this, which is you imagine how would you really measure alpha? It's like you do many black hole evaporation experiments, measure the radiation very, very carefully. Then the toy picture, which I'm borrowing from something Douglas Stanford once told me, is in the gravitational path integral, the page curve calculation, the way it was done was we just were in the Hartle-Hawking state. So we just had these two copies and then we computed the swap test. But now you're imagining that you've done this experiment many times. So there's a lot of black holes floating around, which were from your previous experiments. All of those can connect to the interior of your current black hole by wormholes, right? So whatever the current experiment that you're doing can get a lot of interference from all the other stuff that you did previously. And roughly speaking, that's the thing that would recover the information. But then that's also saying that those previous experiments you did have a large impact on the interior of the current black hole that you're talking about. So that's very firewall-y in that sense. This is a very toy picture. It's just trying to make consistent the fact that there's really no resolution of the information paradox in the sense of you can try to have these like we discussed before, all these souped up versions of complementarity which try to make it better and better. But nevertheless, we never get quite there. Like we still are stuck with some problems. And so if one was to believe that secretly in a single CFT, there is a firewall, this would be a way to make that compatible with gravitational path integral calculations that have been seen. So essentially to say the page curve calculation doesn't imply that the interior is smooth, is one way to say.
And so the conclusion of this is that in n equals 4 Yang-Mills, there is a firewall?
If the bulk theory corresponding to n equals 4 can be quantized using the gravitational path integral, and when you do that, you find that there's no alpha states, there's only one theory dual to it, which is n equals 4, which is what you would believe, then I mean, I don't see how, I mean, it basically undoes a lot of it undoes some of the progress we made from the page curve calculations. You can still treat the page curve calculation as some approximation. So the page curve, the answer that you get for the page curve is still self-averaging. So even if there was no real ensemble that you were averaging over, you just by hand tweaked some matrix elements, etc. That's just your ignorance of the S matrix. You can still use the gravitational path integral as some effective model that's giving you some answer. And since in the page curve case, we can check that it's self-averaging, the variance is small, it's still a trustable answer for the true page curve in n equals 4. But what that means for the interior is unclear. Like, I mean, in order to make that compatible with the interior, we have to go back to ideas like complementarity. And we've seen that that's already pushed us quite far.
And just say one more time. Yeah. So say there was only one alpha. How do I conclude that there is a firewall?
The way you'd see it, roughly speaking, is, so what's the problem with having one alpha? The problem with having one alpha from the gravitational path integral is these connected contributions should not be there. Yeah. So there have to be some other, like if I was doing something like the two boundary calculation, then there should be, I mean, we know that there are contributions which are like the cylinder and they're even on shell and so on. Then there must be other stuff which somehow contribute to the same answer, such that this total sum is just equal to the product of function functions. There must be some other ingredients in that putative bulk theory which cancel out this cylinder contribution and give you an answer which is factorizing. Since they affect this calculation, this is an on-shell closed wormhole solution, which seems pretty fine, but nevertheless, there are other ingredients we believe should be there to cancel that out. Then same thing could happen in the black hole interior. There's no difference.
But couldn't it be something like this Witten's large N averaging was giving you something more?
So the problem with the large N thing is you can still ask, what if I'm in a theory with a particular N?
But that just won't have a gravity description for these questions.
But we still expect that, I mean, so for example, for questions that we would ask in the AdS exterior, we still expect that for a particular N, the answer that we get from the large N limit is a good approximation
for some questions.
For those questions.
Now, low energy questions.
For low energy questions. Here, the issue you would run into is that this, again, I mean, as we said before, like this is a state which is very much in the regime of standard low energy effective field theory. It's very subtle from the perspective of the CFT because it depends on N, like N stuff, which is like, doesn't have a good large N limit.
Yeah.
But nevertheless, from the bulk perspective, it's a very reasonable state. So you'd have to then explain why something went wrong with that. It would still have to be something that's a violation of effective field theory with some ingredients that depend on N in some subtle way. So the picture would not be very different. It would be something very similar to this.
It's different from what you said. I mean, you said that for these questions, there may not be a good gravitational description, right?
No, but for the question of falling into the black hole, there might be a good gravitational description.
I think you'll run into the same issue as we discussed last time. Like even in that case, like there are, I mean, firstly, it's hard to associate a particular area with a particular experiment inside the interior. And so at late enough times, the errors are large. And so even there, like it's not so clear that whatever is the answer for a fixed n should be relevant for that observer. And it's not so clear that it's a self-averaging answer. There can be large fluctuations to that answer itself.
There could be large fluctuations to that answer. It seems reasonable to me that at large n, to try to track down something like the exact state of radiation at any finite n is hopeless within gravity, right? That seems
it's hopeless within gravity, but we hope that at least for some questions which are in the regime of, okay, we have to define what the regime of effective field theory is, but let's say standard Wilsonian, like in the standard Wilsonian sense, any low energy experiment that we do should be described by effective
but it seems to me that the question of what an observer would say as they fall into the black hole, hey, you just send something. That sounds like it should be, that sounds more like it should be a well posed kind of question.
Well posed effective field theory.
At n equals a billion.
Yes.
Okay, and you're saying there's a contradiction with that. I'm trying to understand that.
The contradiction is basically the black hole information paradox. It's the fact that, I mean, it's the firewall paradox, which is that like at any fixed n, you have a fixed theory, you need unitarity. And so what is the thing that really helped you here? The only ideas we had really for that were complementarity.
So you're saying we just don't know the way around it?
Yeah, I mean...
Yeah, like you're saying, we just haven't...
I would say so.
We're back to 10 years ago.
So what can you contrast the learning that we had from the page curve and here? You were saying that it done under some progress that we made. What does that mean?
So the page curve is just a calculation of a number. Right? So the page curve is really just if I try to compute this thing on the boundary
with the islands and so on.
Yeah. So on the boundary, I'm just trying to compute the entropy as a function of time. The bulk calculation involving islands and so on is a very reliable calculation of that number. That I think is fine. And that can work whether or not there are alpha states and so on. Like you can just think of the gravitational path integral as an approximation. And in that regime, you can just test that variance is small. So it's a reliable approximation, even if there's just n equals 4 at a billion. So that's perfectly fine. But the fact that there are islands and there's a semi-classical description we're using to compute this number, etc., doesn't obviously mean that there's actually a smooth experience for an infalling observer. That's the thing that I'm pointing out. It has often been taken to mean that that is not a problem. As we discussed in the different versions of complementarity, there's this claim that the description is fine and up to small errors, the thing that you compute the infalling observer sees is very close to what you can this difference between the EFT inner product and the fundamental inner product is small, for example. So it's not very drastically different from the infalling observer experience. And we'll see that it's not that straightforward as we discuss next time.
So I remember that discussion. Are you tying to this discussion here?
In this discussion, all I'm saying is as a number, as computing that number for the page curve, very good. I don't think there's any issue there. We really need to understand how that translates to understanding what the experience of the infalling observer is.
Is this the difference between Euclidean and Lorentzian calculations? The Euclidean geometry seems smooth, right? In your island kind of calculation.
Yeah.
Okay, but you're saying that for that calculation, there's a smooth geometry, but that may not be the same geometry as an observer.
Yeah, I think we what we don't understand is how to pose the question of how do I read off the infalling observer's experience from the CFT? If I could pose that as a question, then we could fill it in with some geometry and see if that's smooth and etc. and see if the variance of that calculation is small and so on. Then we could believe that. And then presumably that gives us an answer to how this souped up version of complementarity actually works in true gravity, like in a diffeomorphism invariant sense and so on. But just the fact that the number, which is the page curve, was computed using that doesn't really tell us anything about it.
And is there a way we can ask this question?
Yeah.
Let's say that we posit that the guy in n equals 4 at fixed n burns up.
Yeah.
is there something I can calculate in CFT?
Yeah, this is the whole problem. The problem is for interior observables, we just don't know what the right dictionary is. I mean, there's been proposals for it, like there's Papadodimas, Raju, etc. But I don't think, like the extrapolate dictionary is something we can posit and just test very sharply, do experiments and so on, and it's all consistent. We don't have something analogous to that for the interior, because if I send in something, it's not allowed to come out. So I can't make it consistent with the extrapolate dictionary in some sense. So if we did understand that dictionary very well, and really the whole problem here is trying to understand that dictionary. If we understand that bulk to boundary dictionary well, then we could pose this as a CFT question and answer it. I think the status quo right now is that we just don't understand that dictionary. So even if you solved n equals 4 completely, I couldn't answer that question.
Right.
Just because we don't know that dictionary. You could presumably answer it by solving the bulk theory directly and seeing what happens and so on, but I don't know how to do that.
So then at the moment, the kind of arguments are sort of existence of this dictionary runs you into logical contradictions.
Yes. So what people, the way they usually go about it is, let's try to make it as consistent with semi-classical description as far as possible. Does it land us into a contradiction?
Right. But then these arguments you have to get really watertight, because if you can't, if the question is you can't ever get a contradiction just in the CFT.
Yes.
Then it's all a matter of somebody producing a better dictionary might do it, right?
Yes.
So you have to be really clear about that no such thing exists. Those are often the trickiest kind of arguments.
Yeah,
right?
I agree.
This thermal 1-point function thing that Marta said, and
yes.
this seem to probe kind of.
I would say it's similar. I mean, it's similar in the sense of the page curve. So what the page curve does is it computes something which is a boundary quantity, and there is some gravitational description that you get. There's some geometry that you get which is smooth, has an interior, etc., and there's some islands and so on. It computes the correct number using that description. Now, the whole thing we're debating here is whether that description that we saw, which was the smooth description with an interior and so on, is that really what an infalling observer sees, or is that some fiction that helped you compute this page curve? I think you would say the same thing about this thermal 1-point function. Thermal 1-point function is something this asymptotic observer can very well probe and compute whatever you like. There's some analytic continuation, etc., that helps you compute something that seems like it's accessing the singularity, but is that really what an infalling observer would see? And I think it's a similar.
So this plasma ball 1-point function, can we not compute that?
We can compute
that. What exactly? I mean, as a CFT person, right?
Yeah.
If you can predict that it is inconsistent with the bulk physics.
Yeah.
Right. I mean,
let's say
you approximate the trajectory with the semi-classical view, semi-classical path.
Yeah.
And then see whether that the thermal 1-point function picks out exactly that that distance to the singularity, because you also have modeling this evaporation process there, right?
Yes.
So that could potentially be probe.
I think he'll say that that was a trick to do a calculation. I think he'll say that might be a trick to do a calculation from an analytic continuation of the Euclidean metric, but it doesn't say that somebody falling through actually sees it.
No, you as a CFT person, you just measure the thermal 1-point.
You measure it and you get the same answer.
The same as the page curve.
Right? Same answer, but that tells you that there is a nice trick to get the calculation. Nice gravitational trick by involving analytic continuation for this observer. I think he will say that doesn't say that the more interesting question of what somebody falling through that is.
Yeah.
No, but you can try to see at least whether this kind of thinking is what is it predicting.
Yeah.
Whether it is predicting.
I mean, the interior is clearly useful for computing things. Like the page curve is a good example of it, right? Like it's giving you an accurate answer of what you would have computed in the CFT for that purpose. Now, the question is really only whether the bulk experience is consistent with that. All right.